Now we will discuss different forms of representation of state equations and discrete time systems. Now our difference equations in the state space analysis is x of k plus 1 is equal to a into x of k plus b into u of k, and y of k is equal to c into x of k plus d into u of k. As you all know, A is the system matrix, B is the input matrix, C is the output matrix, and D is the direct transmission matrix. Now different forms of representing these state equations or output equations we will be discussing now based on this discrete time difference equation. Let us consider a difference equation of a linear time invariant system in the discrete time domain. The difference equation, let us say y of k plus a1 y of k minus 1 plus a2 y of k minus 2 plus so on plus an y of k minus n is equal to b naught u of k plus b1 u of k minus 1 plus so on plus bn u of k minus n. For example, let us consider this linear time invariant system which is represented in the difference equation form, and k is from 0, 1, 2, so on up to infinity, where k is the various instants of time. Now when you apply Z transforms, to this equation, what do we get? Applying Z transforms to this entire equation, you have, by linearity theorem, you can say Z transform of y of k, Z transform of a1 into y of k minus 1 and so on, and which is equal to Z transform of b naught u of k and so on. So every individual term factor can be Z transformed. Therefore, Z transform of y of k, as per the definition, we have y of z plus a1 is a constant, so we can take it out without any problem, and because we have this linearity theorem, and Z transform of y of k minus 1, a time delayed Z transform, we have already proved that theorem, so it is Z inverse y of z plus a2 Z transform of a2 into y of z power minus 2 y of z plus so on an into z power minus n, you have this one z power minus n y of z is equal to b naught u of z plus b1 z power minus 1. For this relationship you get Z transform, you get u of z here, z inverse plus so on plus bn z power minus n u of z. Now if you consider taking common in on both left hand side and right hand side, y of z is common here, so y of z, when you have considered it common, you can say you have 1 plus a1 z inverse plus a2 z power minus 2 plus so on an z power minus n, which is equal to, when you consider u of z common, into b naught plus b1 z inverse plus so on plus bn z power minus n. Now what is the pulse transfer function for us? Pulse transfer function is defined as the ratio of the Z transform of the output variable to the Z transform of the input variable. Right. So we have this as the pulse transfer function, which we have discussed in our earlier classes about pulse transfer function. We have y of z by u of z. Now in this equation y of z by u of z, you have b naught plus b1 z inverse plus bn z power minus n divided by 1 plus a1 z inverse plus a2 z power minus 2 plus an z power minus n. So this is your pulse transfer function, and I can consider this to be equation 1. This can also be represented, we have all the negative powers of z. Now if you convert it into positive powers of z, that is if you multiply z power n and z power n here in both the cases, multiply and divide with z power n, you have b naught z power n plus b1 z power n minus 1 plus so on bn by z power n plus a1 z power n minus 1. If you are multiplying everything, you have a2 z power n minus 2 plus so on an. So you can consider this to be equation 2. Okay, so different forms of representation of state equations. Now we will come into, for this pulse transfer function y of z by u of z, for this sort of a pulse transfer function, for any linear dynamic system, time invariant system represented in difference equations, the pulse transfer function can be of any of these two forms. Right. So these equations, if you wanted to convert into state model equations, you wanted to convert it into x of k plus 1 is equal to a xk plus b uk, or you can, we have already used g and h u of k, and y of k is equal to cx of k plus du of k. Right. So this pulse transfer function has to be converted into this form. That is x of k plus 1 is gx of k plus hu of k, and y of k is equal to cxk plus duk. You have many different types of forms that are available if you can find a particular matrix and convert it into different forms of representation. But basically we have 4 different types of or different forms of representation of state equations, which we will see now. And those are, first one, the controllable canonical form, which can be obtained from the direct programming method. Direct programming method, which in this lecture I will not be dealing with this direct programming method. I will give you the direct, the controllable canonical form of representing state equations right in this lecture, but we will discuss direct programming method in the next class. And we have this observable canonical form. With this can be obtained by using the nested programming method, which again I will be dealing in the next forthcoming lectures. And the third is the diagonal canonical form, and the fourth, Jordan canonical form of representing. So these are the 4 different types of representations of state equations in the discrete form or in continuous term, and these 2 can be obtained from the partial fraction expansion method. Partial fraction expansion method. Right. So we have 4 different types of representations here. The controllable canonical form, the observable canonical form, the diagonal canonical form, and the Jordan canonical form, which can be obtained by, the controllable canonical form can be obtained by direct programming method, observable canonical form can be obtained by the nested programming method, and these 2 forms of representations, diagonal canonical as well as Jordan canonical form, can be obtained by partial fraction expansion method. So now we will try and understand what are the, now in this representation, the state model equation, we need to know what are G, H, C and D matrices. So how do we get the matrices, the elements of the matrices G, H and C and D from this pulse transfer function? From this pulse transfer function y of z by u of z. So we have only coefficients b0, b1, bn, a1, a2, an. So from these coefficients, how do we get the matrices here G, H, C and D? That is what we are going to see in this controllable canonical form, observable canonical form, the diagonal canonical form and the Jordan canonical form. So let us first go with the controllable canonical form of representing the state equation. So what is the controllable canonical form? I will directly give you that. As I have stated earlier, I will be discussing the direct programming method in the next class. Only thing I will have to, now I will be discussing only the controllable canonical form, the output equation that we are going to have here. So x of k plus 1 is a vector. It is a vector. It means that it is an n by 1 vector of n variables. So x1 k plus 1, you can say x1 k plus 1, x2 k plus 1, x3 k plus 1, so on, xn minus 1 k plus 1 and xn k plus 1. So this is our left hand side x of k plus 1. This x of k plus 1 is here, which is given as per our controllable canonical form. The controllable canonical form is given in this way: 0, 0, 0, 0, 1, 0, 0, right, and again 0, 0, 0. Here you will have a 1 again, 0, 0, and if I go down, I will have 0, 0, 0, 0 and 1. Here in the last column, you will be having values of the denominator of the pulse transfer function, which is minus an minus 1. You can have here minus an minus minus 1 minus minus 2, so on up to minus a2 minus a1. You have up to this value minus an minus 1, so on, minus a2 minus a1. So this is our system matrix A. Okay. Okay. So this is our system matrix A. The entire matrix you can go with x1 of k, x2 of k, x3 of k, xn minus 1 k, xn k. So this x of k plus 1 is this vector, the state vector, the difference equation of the state vector. G, matrix G is this vector, which is, you can see from this diagram, you can see that now this, you can see here, this is a unit matrix of order n minus 1 by n minus 1. You can see this. The remaining elements all are here zeros, and the bottommost row you will have values from minus n minus an minus 1 minus a2 minus a1. Right, and you have this. So this is the controllable canonical form, and the output, the input matrix, you have it here 0, 0, 0, 0 and 1 u of k. Right. So this is H matrix, this is H, this is system matrix G, right, and this is an n by 1 vector, this is n by 1 vector, so n by 1, and that is u of k, right, n by 1 into 1 by 1 if you have. So you will have, for example, let us say you will have only, this is 1 by 1 and n by 1 you have n by 1 here, this is n by n, and this is n by 1. You have n rows and 1 column, n rows and n columns, n rows in 1 column, n rows in 1 column. So you have this representation, right? And now we need to go for y of k, where you will have to find out what are the C and D matrices. So y of k, y1 of k, y2 of k, y3 of k, so on up to yn of k. For example, if we have it like this, which is nothing but is equal to, or you can simply say, if you go for a single output, you can say it is y of k, which is nothing but bn minus an b naught, bn minus 1 minus an minus 1 b naught, so on, b1 minus a1 b naught. So you have n variables here, and the system is x1 of k, x2 of k, so on, xn of k. You have n variables, so you have here 1 by n and you have here n by 1. So this is 1 by 1, and you have this 1 by n into 1 by n plus b naught uk. Plus b naught uk is the term you are having. So this is controllable canonical form of representing a state equation, right? So this theorem we will be discussing in the further classes. The theorem or the proof of this will be discussed in the further class, which is obtained by the direct programming method. Okay. Now for this, from this equation itself, which we have obtained for controllable canonical form, you can also obtain the observable canonical form. So I put the heading as observable canonical form of representing this equation, where you can see that this matrix G will be the transpose of the controllable canonical form. In the observable canonical form, the matrix G must be the transpose of the controllable. Now this is a controllable canonical form. Now what is the transpose of this matrix? When you are trying to remove this, what is the transpose of this matrix? 0, 1, 0, 0, 0. You will have this in the column, and this will be the second column. The third row will become the third column, and so on. Therefore, you can say that we can simply change this into 0, 1, 0, so on, 0, or you can say you have 0 here, then 0, 0, 1, 0, 0, and 0, 0, 0, 1, and so on, zeros, right? And you have here 0, 0, 0, 0, and here you have 1, right? And here the last column you have minus an minus 1, an minus 2, minus a2, minus a1. Now this is your G matrix, which is the simple transpose of the matrix, the system matrix in the controllable canonical form. So the matrix, system matrix in observable canonical form is simply the transpose of the system matrix in controllable canonical form. And here, what is the equation here in this H matrix? The H matrix is the transpose of the output matrix in controllable canonical form is the input matrix in the observable canonical form. That is, you can say you have here Bn minus An B naught, Bn minus An B naught, Bn minus 1 minus An minus 1 B naught, Bn minus 2 minus An minus 2 B naught, so on, B2 minus A2 B naught, B1 minus A1 B naught into U of k. So this is your state equation of the observable canonical form, which is obtained from the controllable canonical form. Now what is the matrix here? The input matrix here. That is also the transpose of the input matrix here in the controllable canonical form, which you have it here as 0, 0, 0, 1 into x1 of k, and the D matrix remain as it is. So now you have these two equations for the observable canonical form, right? So one thing which we can say, for the observable canonical form, you can derive that equation with the nested programming method. For the observable canonical form, you can derive these equations using the nested programming method, right? So you can easily say that the system matrix, or in short you can say, if you have CCF and OCF, right? In the CCF you have the system matrix G, H, C and D. Here OCF you have G transpose as the, if you have G cap or G naught as the system matrix, then G transpose is G naught, and you can say H cap or H naught is nothing but C transpose, and C naught is nothing but H transpose, and D naught is D. Right. So using these equations, you can get, using this formula, you can get the observable canonical form from the controllable canonical form. Now we will discuss the diagonal canonical form. And the Jordan canonical form. Diagonal canonical form and Jordan canonical form. For example, in this given transfer function y of z by u of z, or the pulse transfer function y of z by u of z, we have different equations: z power n plus a1 z power n minus 1 plus an, and b naught z power n, b1 z power n minus 1, so on, plus bn. Right. This is the pulse transfer function of the given linear dynamical system or linear time invariant difference equation represented in discrete time systems. For this, if the poles, that is the denominator, the poles, the roots of the denominator, which are all distinct values, then you will be having diagonal canonical form, which is as simple as this, that is x of k plus 1, or you can say x1 k plus 1, x2 k plus 1, so on, xn k plus 1. Always we will be considering n number of state variables, which is nothing but all distinct poles that are with values p1, p2, so on, pn are the number of poles. You can say all those will be the diagonal elements pn, x1k, x2k, so on, xnk. So you have this as all the distinct poles you will be having in this way. So the diagonal elements are all the distinct poles, and the upper triangular matrix and the lower triangular matrix of this matrix are all zeros. So you have this plus 0, 0, 1 u of k, right? So you have this equation as the diagonal canonical form. Now if any case when you want to go for the Jordan canonical form, that is, if we have poles which are not distinct but equal. For example, let us say m poles are equal in m number of poles are equal, and the remaining poles are, that is, P1 is equal to P2 is equal to so on is equal to Pm. Then you have Pm plus 1, Pm plus 2, so on Pn. So you have n number of poles, and if you are having it like this, then you can go for this equation. So on xm k plus 1, then xm m plus 1 k plus 1, so on xn k, xn n of k, which is equal to, you can have this P1 1 0 0, so on okay, P1 1 0, or you can say this as like this 0 0, right? You can say, I'll try to divide this into equal parts here, so that we have all these values P1, P, all these Pm values you can consider it to be a single value P1, then 0 0 0, the last value P. Okay, then again we have this, all these values are zeros. Okay, and here you have P m plus 1 0 and Pn 0, and you have all these zeros. Right, x1 k, x2 k, xm k, xm plus 1 k, and xn k. So you are having these values, you will be having all the diagonal elements. So this part you have the diagonal part, and this is called the Jordan block, right, of this system. So these are the 4 different types of representations of state equations. Therefore, once we have finished with this, we can say that, we can understand that any one system equation, any physical system can be represented in different forms, the same equations, the same x dot x of k plus 1, x of k plus 1 is equal to g x of k plus h u of k, and y of k is equal to c x of k plus d u of k. This state model equations can be represented in various forms, that is in the controllable canonical form, that is in the observable canonical form, diagonal canonical form, Jordan canonical form. So different forms of representing a particular equation, that is which are representing any one particular physical system. So you have different forms. So you can call it as non-uniqueness of representations of state equations for a given system. So anybody can design any form of representing state equations. Not a single method is available. You can get different types of state equations for a single system. Here let us say we can go for, now when you apply Z transforms to these two equations, so Z transforms of x of k plus 1 is equal to Z transform of G into x of k plus Z transform of H into U of k. Similarly we have that. So Z transform of x of k plus 1 will give us Z into x of z, which is minus z into x of 0. Let us say for instance we are considering x of 0 as 0, and you can say G is the system matrix, which is a constant, Z into x of z plus H into U of z. Similarly, when you are applying Z transforms to this, you will get y of z is equal to C into x of z plus D into U of z. Now when you are having this, and you can represent this here, now this equation Z into x of z, capital G into x of z, you can get Z into I. Because these are matrices, I cannot simply go with Z, I should go for identity matrix I. So when I take x of z and x of z on one side of this equation, I will be having Zi minus G into x of z is equal to H into U of z. Right. So what is x of z from this? X of z, now Zi minus G is a matrix, and inverse is possible only when this is non-singular in nature. So Zi minus G should be non-singular in nature. X of z is equal to Zi minus G whole inverse H U of z. Zi minus G whole inverse H U of z. So if I replace that, this equation is replaced here in the output equation, you will be getting y of z is equal to C into Zi minus G whole inverse H into U of z plus D into U of z. So you will be getting, when you take U of z common, C into Zi minus G whole inverse H plus D into U of z. So this is your y of z, and you can get the pulse transfer function from this. Y of z by U of z is C into Zi minus G whole inverse H plus D. So when going into the non-uniqueness of representation of state equations for a given system, you can go for, once this is obtained, you can go for this equation. With the same equation, you can see that your non-uniqueness of representation, you can have different types of representations: controllable canonical form, this observable canonical form, diagonal canonical form, and Jordan canonical form. And if we can design some vector x cap of k is equal to G into P, or you can represent it P into x of k. For example, x cap of k. Now I want to convert this into a different form, x cap of k. so far we were having x of k. Now we can go for x cap of k is equal to p into x of k, because x of k is known to us. P is any non-singular matrix. P is any non-singular matrix which can be determined. Therefore, x cap of k, if we consider this x cap of k plus 1 is equal to p into x of k plus 1. When I am replacing k with k plus 1, here I can replace k with k plus 1. I will get this equation x cap of k plus 1 is equal to p into x of k plus 1. Therefore, when we have x cap of k plus 1 is equal to g into, or I have a small change in this. In fact, it is the other way around. X of k is equal to p into x cap of k. Therefore, you can have x of k plus 1 is equal to p into x cap of k plus 1. Now, if I replace this in this equation, I will be having p x cap k plus 1 is equal to g into, what is x of k? We have p into x cap of k plus h into u of k. P into x cap of k plus 1 is equal to g into p into x cap of k plus h into u of k, which you can see this. X of k plus 1 is p into x of k plus 1. X of k is p into x cap of k, right, and hu of k is hu of k here. So we are having this equation, and p into x cap of k plus 1, if you are having this, and if you pre-multiply, if we pre-multiply on both sides of this equation with p inverse, and we have already mentioned that p is a non-singular matrix, therefore P inverse exists, because det P is not equal to 0. P inverse exists. Therefore, if I pre-multiply with this, P inverse P, P inverse GP, P inverse H, when you are pre-multiplying with this, what do we get? P inverse P is an identity matrix, so I can have I into x cap of k plus 1 gives us again x cap of k plus 1 is equal to P inverse GP x cap plus P inverse. Now if I say G cap is equal to P inverse GP and H cap is equal to P inverse H, then I can write this equation as x cap of k plus 1 is equal to G cap x cap of k, because P inverse GP is nothing but G cap into x cap of k plus P inverse H, it is H cap, this entire thing is H cap into U of k. Right. So we are having this equation, you have obtained this equation to this equation, and once again for y of k plus 1, if we can derive it here, the y of k plus y of k is equal to c into, what is x of k? It is p into x cap of k. Cp x cap of k plus d into u of k. D into u of k. So y of k, now the new output equation y of k is c cap x cap of k plus d into u of k. Now c cap is equal to c into p and d is equal to d, or d cap is equal to d. If I can write d cap here, d cap is equal to d. So if you can have p, you can see that what are the various equations that we are getting? Non-uniqueness with this transformation, that is x of k is equal to p into x cap of k with this transformation, where p is the transformation matrix which is non-singular. P is a transformation matrix which is non-singular. If this transformation is possible, that is, if you can find the P which is a transformation matrix, then you can transform this system into another system where we are having x cap of k plus 1 is equal to g cap of x of k plus h cap of u of k, and y cap of k is equal to c cap x cap k plus d cap u of k, where g cap is equal to p inverse gp, h cap is equal to p inverse h, and c cap is equal to cp, and d cap is equal to d. Right. So this equation and this equation are two different equations with the help of this transformation. X of k is equal to p into x cap of k, which is the transformation where p is the transformation matrix which is non-singular, and if you can find out p an infinite number of times, p can be found in a different ways, different forms of p can be obtained, and for different p transformation matrices, you will get different state equations for the same equation or for the same physical system. Therefore, the state space representations are non-unique in nature. Representing state equations for a given single system is non-unique in nature. That is, if you are having p, if you can find p, the transformation matrix, in such a way that you can get different forms of representation, either in any of these forms also can be represented, and most importantly diagonal form p inverse gp. If you can find p in such a way that p inverse gp is an diagonal matrix, then you can have the diagonal canonical form in this way. So these are the various types of representations of state space equations.